we have to draw binding energy per nucleon versus mass number graph. Binding energy per nucleon versus mass number graph. We have to draw binding energy per nucleon versus mass number of an element curve or graph. So we are going to draw binding energy curve. We are going to draw binding energy curve. So we can draw two mutually perpendicular axes. One axis is vertical axis, and along the vertical axis we can denote the different amount of binding energy. 9 mega electron volt, 8 mega electron volt, and it will be 4 mega electron volt, and these are the different values of binding energy. And binding energy is the energy due to which nucleons are bound inside a stable nucleus. Now we can denote 2 mega electron volt binding energy, and this is, and again here we can denote 1 mega electron volt binding energy, then 3 mega electron volt, this will be 5 mega electron volt, and this is 7 mega electron volt. And along the vertical axis we can denote binding energy per nucleon. So along this vertical axis we are plotting binding energy of a nucleus per nucleon, binding energy of a nucleus per nucleon. That means binding energy per nucleon is plotted along the vertical axis. We are plotting binding energy per nucleon of an element along this vertical axis, and we have denoted the different values of binding energy from 0 mega electron volt to 9 mega electron volt. Mass number of the element, that is capital A, is plotted along the horizontal axis. We have plotted an imaginary line parallel to mass number axis having value 8 mega electron volt, and also we can denote 8.8 mega electron volt. 8.8 mega electron volt, and this line will be an imaginary line indicating binding energy per nucleon of 8.8 mega electron volt. This is an imaginary line parallel to mass number axis, at which the value of binding energy per nucleon will be 8.8 mega electron volt. We can denote different values of mass number on the horizontal axis 240, and then it will be 120. This mass number will be 120. Then this will be 60. Mass number, the value of mass number at this point will be 60. Then we can denote 40 and also 20. 20 is another value of mass number. At this point the value of mass number is 20, and then we can denote the mass number of 40 at that point, and this will be 10. That is the value of mass number. Now we can denote the mass number 5 and 2 on the horizontal axis, and also we can denote a point at which now we can denote H2 or hydrogen nucleus at this point, having binding energy per nucleon as 1.1 mega electron volt. And for binding energy curve, we have to memorize the nuclei of the following element, that is, we have to denote the position of different elements H2, He4, Li7, C12, N14, O16, that is oxygen, fluorine 19, and lastly iron 56. Fluorine 19 and iron 56, and lastly uranium 239. Fe56, that means we have to also denote the position of Fe56 or iron nucleus on this binding energy curve. After Fe56, we have to denote the position of uranium 239 nucleus. Now we can draw an imaginary vertical line having mass number 5. This is the imaginary line or vertical line, and at which mass number is 5. Now we can denote the position of helium nucleus. This point is indicating the position of helium nucleus or He4. And now we can draw the graph between H2 and He4. We can draw the graph between hydrogen and helium nucleus. The graph will be moving upwards from H2 He4, and now we can denote the position of lithium nucleus or position of Li7. And binding energy of helium nucleus or binding energy of He4 is 7 mega electron volt. This point is indicating the position of lithium 7 or Li7 nucleus, and we can draw the graph between the points indicating the position of helium nucleus and lithium nucleus. Now we can denote the position of lithium nucleus. 7 is the value of mass number, and we can denote or we can draw a vertical line having mass number 7, and also this point is indicating the position of lithium nucleus or Li7. Now we can draw the graph between helium 4, He4 and Li7. To denote the position of carbon nucleus or C12, we have to draw imaginary vertical line having mass number 12. This is the imaginary line parallel to binding energy per nucleon axis. And this vertical imaginary line indicates the position of carbon nucleus. That means this point is indicating the position of carbon nucleus or C12. Binding energy of carbon 12 maybe 7.6 mega electron volt, and we can denote or we can draw an imaginary vertical straight line having mass number 14 to denote the position of nitrogen nucleus. Here this point is for nitrogen nucleus or N14 nucleus, and we can draw the graph between C12 and N14. Now we can draw an imaginary vertical line having mass number 16, and we have to draw this imaginary vertical straight line having mass number 16 to denote the position of oxygen nucleus or O16 nucleus. This point is for oxygen nucleus or O16 having binding energy 8 mega electron volt, and we can draw the graph between nitrogen and oxygen nucleus. So we have drawn the graph between N14 and O16 nucleus. Binding energy of oxygen nucleus is 8 mega electron volt. That's why the point indicating the oxygen nucleus has the binding energy 8 mega electron volt. And also we can denote an imaginary line having mass number 19 to denote the position of fluorine nucleus or F19. And we have drawn the graph between oxygen and fluorine nucleus, and binding energy graph is drawn from hydrogen nucleus to fluorine 19 nucleus. Now we can denote an imaginary vertical line having mass number 56 to denote the position of most stable element, that is iron 56. This is the position. This point has the binding energy 8.8 mega electron volt, and we have drawn the binding energy graph from fluorine to iron 56. This point indicates the position of iron nucleus at which binding energy per nucleon is 8.8 mega electron volt. 8.8 mega electron volt. Now we can denote an imaginary vertical line having mass number 239 to denote the position of uranium nucleus. This point is indicating the position of U239. Now we can connect iron and uranium 239, or we can draw the binding energy curve between iron and uranium nucleus. Now we can draw binding energy curve between iron and uranium nucleus. This is the binding energy curve between iron and uranium 239 nucleus. Here iron exists at the highest position of binding energy curve, having maximum value of binding energy. That's why iron is most stable element. Most stable element is iron 56. According to the binding energy per nucleon versus mass number curve, according to the binding energy curve, binding energy per nucleon versus mass number graph or curve, according to the binding energy per nucleon versus mass number curve or graph, it is observed that iron under bracket Fe26 iron 56 has the maximum value of binding energy per nucleon. Iron 56 has the maximum value of binding energy per nucleon. iron 56 has the maximum value of binding energy per nucleon, and that maximum value of binding energy per nucleon is 8.8 mega electron volt. Iron 56 has the maximum value of binding energy per nucleon, which is 8.8 mega electron volt. On the binding energy curve, Fe56 exists at the highest point, and binding energy per nucleon for Fe56 is 8.8 mega electron volt, which is denoted on the binding energy curve. It means that iron 56 is most stable nucleus or element. Most stable, it means that iron 56 is most stable nucleus, that is most stable element or most effectively bound nucleus. Iron 56 is most stable nucleus, that is most effectively bound nucleus. Iron 56 is most stable nucleus, that is the most effectively bound nucleus. On the curve, Fe56 exists at the highest position. That means Fe56 has maximum binding energy. That's why it is most stable nucleus or element. And this is the binding energy curve. And we can say another conclusion, that now we can also say that binding energy per nucleon for He4, binding energy per nucleon for He4 is greater than the binding energy per nucleon for lithium 7. Binding energy per nucleon for He4 is approximately equal to 7 mega electron volt, but binding energy for lithium 7 is 5.5 mega electron volt. That's why you can say that binding energy per nucleon for He4 is greater than that of Li7. Here, hence we can say that He4 is more stable than lithium 7. Though He4 has less mass number, though He4 or helium has a less mass number, He4 has binding energy 7 mega electron volt. Binding energy per nucleon for helium 4 or helium nucleus is 7 mega electron volt, but lithium has binding energy which will be equal to 5 mega electron volt or 5.1 mega electron volt. Binding energy per nucleon for lithium 7 nucleus is 5.1 mega electron volt, as binding energy per nucleon for helium is 7 mega electron volt, which is greater than the binding energy of lithium 7. That's why though helium has lesser mass number, but helium is more stable than lithium. Binding energy per nucleon for helium 4 is greater than the binding energy per nucleon for lithium 7. Therefore, stability of He4 will be greater than the stability of lithium 7. For mass number ranging from 2 to 20, the mass number ranging from 2 to 20, On the graph for the mass numbers ranging from 2 to 20, there are sharply definite peaks or sharply defined peaks. There are sharply defined peaks corresponding to He4, C12, O6, O16, O16, etc. Not F19, it should be only He4, C12 and O16, etc. This peaks indicate that this peak indicate that these nuclei are relatively more stable. These nuclei are relatively more stable than the other nuclei. Relatively more stable than the other nuclei in their neighborhood. The peaks indicate that these nuclei are relatively more stable than the other nuclei in their neighborhood. For the mass numbers ranging from 2 to 20, there are sharply defined peaks corresponding to He4, C12, O16, etc. These peaks indicates that these nuclei are relatively more stable than the other nuclei in their neighborhood. This peaks on the binding energy curve. This peaks on the binding energy curve indicate that helium, carbon, oxygen are more stable with respect to lithium, nitrogen and fluorine.